We have time for a few questions, so please type them in the Q&A group using your chat tab. One of our first questions is, how long do you think it will take to get to the point of producing actual commercial solar cells with materials found with this project?
Well, if we are very optimistic, some of the molecules that we already have found could be synthesized, again, in the time span of a year or two, and characterized, and then transferred to industry. So there's already commercial companies that are trying to build these materials, so it will be just a question of trying to convince them to use these high percentage molecules, if when they are characterized, they really turn out to be 10% efficient.
Okay, we have another question. Can you explain on a basic level how the computer resources have been used?
Well, you saw that database that we're building with 1.5 million calculations. Every time you download a work unit, actually 1.5 million molecules, each one composed of about 10 to 20 individual QChem calculations. Every time you download one of the work units, you download a molecule. That molecule is run in these 10 to 20 calculations, sent back to us, and the plot that I showed you at the end is actually a collection or aggregation of all those different molecules. And the 4 I showed you by chance, were some of the ones that one of you guys computed. So that's how the resources are used. They're running quantum chemistry calculations on a molecule.
And we have another question. Are costs of material a problem?
The point of cost of material, yes, making plastics is cheaper than making silicon. Why is that? Because for making silicon, you have to melt this thing and purify it, whereas making a plastic is very much, low temperature processing. So in general, making plastic, the same amount of weight of plastic is cheaper than making silicon. It depends on the molecule. It's more what is going to be the durability of the molecule. It's more what is going to be the manufacturing process. But in general, people believe that if we raise the efficiency of organics, which are cheaper, to around 10%, then you can compete with silicon solar cells. You can even think about making solar paint or solar spray paint, okay? Because this is just plastic. Okay, so that's kind of more ahead, but really think about cheaper materials.
We have another question. It's a little more technical. Would this same process be useful for CIGS or cadmium telluride photovoltaics?
You could imagine doing calculations like this for solid-state materials. We don't do that. There is a person called Gerbrand Seder at MIT that does not use a grid but uses a supercomputer, and he's actually building what he calls the Materials Genome Project, where he's actually trying to find out materials for batteries and also perhaps for these solar cells. We don't concentrate on solids, but surprisingly enough, yesterday I was discussing this at chemical engineering at UC Berkeley. I was giving a talk yesterday, 2 days ago, and we were discussing this as well. So perhaps one day the Clean Energy Project could expand to solids. Right now we're just concentrating on organics. They are keeping us very busy.
Another question, will your results be open and subject to intellectual property?
Yeah, eventually all the results will be released to the public. Well, we're waiting. Of course, our database is not ready. We're analyzing the results. So there will be a time lag between analyzing the results and then providing them to the public in a database that is fully searchable by the research community.
What is the lifetime of these plastic cells? Is it durable? Will they last 20 years?
Well, that is the issue that we need to figure out. Probably they're going to be not lasting 20 years, but they will be so cheap that you can replace them every few years without, for example, changing the backport of your solar cell, but just changing the plastic. These are issues that are still up in the air. But if you don't have an accelerated Manhattan Project style project like this one, which you really go all the way full blast into finding the new materials, we won't find out. But Conarca, one of the companies that produces these polymer solar cells, is already selling them, so I am assuming they have a reasonable lifetime.
What is the next milestone for your project?
Well, there are many milestones that are coming up, but the immediate next one is that we're going to be using the TeraGrid, the National Science Foundation supercomputers, to do higher, more sophisticated calculations that we cannot run in the grid right now yet. So we have 4 million hours of computer time on these top 10% molecules. That's an example. While we keep scanning in the Clean Energy Project using the grid, other families of molecules. So another milestone, the next one that comes up, is to feed in new families of molecules based on the information that we have already.
When do you expect to exceed 10% efficiency?
As I told you before, if we are very optimistic, Some of the molecules that we already have might be characterized, and they might have 10% efficiency already, if we walk the talk, right? So we'll see. Perhaps we find out that for a particular reason, one of our predicted molecules does not have 10%, so we have to try another one. But definitely, we have some of them already that, according to our predictions, should be 10%. Now it's just a question of interacting with experimentalists to make it a reality.
Okay, some solar cells use a combination of materials to extract energy from different parts of the solar spectrum. Is it possible, or maybe easier, to do this with polymers?
Yeah, I mean, these molecules that we're computing are actually oligomers for building blocks for polymers. I forgot to say this. So when I say molecule, I'm really thinking polymer or molecule. Yes, these are called tandem solar cells. You can imagine having a solar cell that has two different layers, which each one absorbs different colors of the spectrum, and this has been demonstrated with organics. So yes, we imagine that perhaps the final devices will be tandem solar cells.
And we have one more question. Would it be possible to work backward from some ideal theoretical material structure and then try to design a compound that has that required property?
Well, that's kind of like we're doing here, okay? It's learning the design principles, and perhaps if everything is successful, when you have all the design principles and all this search, from the search we can inform ourselves how to design materials. So if you saw our big picture, there was a molecular design part that was not in yellow yet, because we haven't started on this, but that's in our plan. Yeah, our building blocks come from actually somebody thinking about how to build, the material. So our experimentalists told us these are the building blocks that if combined will give us probably. So there is human thinking here. It's not just a random search. Okay, humans we're always moving this search around. So it's not barbaric, but it's actually we're thinking about it. But we need a lot of computer time to be able to do the search, and that's why we use the work community grid.
Okay, well, it looks like we've answered all the questions that have come in. So thanks again, Alan, and those attending. Sorry if we didn't get to any questions that you might have still been thinking about, but you're welcome to post those questions in the forum on our site at worldcommunity.org under the Clean Energy Project, and researchers will do the best to answer those. So thank you very much, everybody, for attending. This concludes the question-answer portion of the webcast.
We hope that you have enjoyed today's webcast. The presentation and question and answer session will be made available on YouTube. An email will be sent out to the members when the replay of the presentation has been made available. This now concludes the webcast. Thank you for participating.